All right. Let's start. All right. So welcome to class, everyone. Today's March 24th, 2021. So some housekeeping notes. So Adriana, it is April 5th, right, dear?
Yeah.
Test 3, April 5th. I'm tentatively planning for that, and it's going to
That's the day after Easter Sunday.
Day after Easter Sunday. That's probably not a good day.
I don't know how many people are going to show up.
It's all online.
Okay.
It's all at home, but I believe Easter is a big holiday. Okay, hold on. It's going to cover chapter 15 and chapter 16. And I think I'll change that to the 7th. Okay, so we'll change it because of the Easter ceremony. So I'll update Canvas and all, but we'll change to the 7th because Easter, Sunday, everyone is, even if I have office hours, who's going to come on Easter Sunday office hours? That's not good. So thank you, Adriana, again. So we'll change this to April 7th. It's the exact same format as the previous other two tests. Okay, the averages for those tests are like the 80s, 82, 83. So it'll be changed to Wednesday, April 7th. I already made the study guide. I made the study guides for everything except test 4. So if you want a heads up of what will be on the exam, please check the study guide that's on Canvas. So, all right, so we'll probably have the review if you come to class. We will have class. We'll have the review April 5th. Sunday's Easter, so April 5th review.
I was about to say we get Friday off, so we wouldn't even be able to review the Friday.
Right. Friday. Is Thursday a holiday?
Thursday's a holiday and Friday's a holiday.
Thursday's rest day, and then Friday's Easter, Good Friday, Sunday's Easter Sunday, and so.
Easter Monday,
Easter Monday we'll have class, but it will be recorded and we'll have a review. And then April 7th will be on the exam. All right, so study guide on Canvas. All right, I'll, for those of you watching this later on, I'll update Canvas. But having a test after Easter Sunday, I don't think is a good idea. So I didn't realize it until now. All right, so that's our test 3. Okay, it's a multiple choice and a problem set. Okay, just as before. And also, the way my system works, your quizzes are going to be due on the same day as the test. So quiz 3 will now be due on April 7th. All right, so please make a note of that. All right, quiz 3. So start working on quiz 3 incrementally. All right, at your own pace, so that at that time you'll be able to upload it to Canvas. And by the way, I do drop one quiz. So quiz 1, quiz 2, quiz 3, quiz 4, I drop one of the quizzes. Start working on homework 16. All right, I think I made videos for all of these homework problems, so you can use that. You can use the answer key posted on Canvas. Homework is just practice. All right, it's good to do some chemistry problems. And lab, so there's a lab report due on Le Chatelier's principle. So that's over. We're not doing this. Last week was the last week, and then a lot of you have not turned in the rates of reaction lab report. Okay, some of you have, some of you haven't, but if you have, good. If you have not, turn that in and I'll put some points. Okay, some points are better than nothing, so please turn that in. And this Friday we'll have a problem set. Okay, so this Friday work together, work with your lab partner, check your answers with mine, and do the titration problem set. So no lab. All right, and also as a final reminder, update your lab notebook. Okay, I'll turn that in at the last day of class, last day we meet, which is coming up pretty soon. Okay, semester is almost over. So update your lab notebook, give that to me, and I'll give you 100 points. All right, free 100 points. Yes, Josh?
Do you want the problem set in the lab notebook?
No, I do not. Okay, no, thank you. Good question, I agree. All right, so I have some spare lab notebooks if you want to remind yourself of how we do lab notebooks. Okay, it's just the same as we've done in all the professors. In chemistry, same lab notebook format. Also do clutch prep. So I got an email from the clutch prep person. She said 4 of you are doing it. So, okay, good. So make sure you do that. I'll give you some extra credit. She said 4 are doing it. One of them is not doing it or stop caring or do whatever. It don't matter to me. It's really, I put that to help you learn. It's your $30, so put it to good use, and I'll give you some extra credit for your time and effort there. And I think that's all I have. All right. So, all right. Let's review Monday. Review Monday's lecture. The first thing I want to review for you guys is this idea of buffers. Okay, so when you think of a buffer, it's going to be something that's going to keep the pH stable. Okay, pH is minus the log of H plus concentration. It's going to keep the pH stable. Actually, our body's pH is around 7.4 or so. If you go above 7.4, it could be a problem. Go below 7.4, could be a problem. Okay, so our body has its own buffer system to keep the pH at in check. So buffers in the general chemistry context, not biochemistry or physical chemistry, but in general chemistry is going to be some combination of a conjugate acid with a conjugate base. Okay. It's going to be, I should also say, a weak conjugate acid with a weak conjugate base. So why is there no strong acid? Okay, why is a buffer not strong acid with strong base? Anybody want to speculate why it's not a combination of strong acid with strong base? They will neutralize each other. That's perfect, right? So the strong acid will eat up the strong base. Okay, the strong base will do the same to the strong acid. Okay, so they eat each other apart. Okay, why is a buffer not? Why is not a buffer a strong acid with a weak base? Why is that not a good combination for a buffer? Right, the strong acid would eat up all the weak base, So this is not a good combination for a buffer. And then finally, a buffer is not a weak acid with a strong base. Okay, why is this not a buffer? Because the strong base, what will it do? Okay, strong usually dominates weak. Okay, the strong base will totally destroy, neutralize, capture the weak acid. So these are not good buffers. Okay, the buffers are going to be the weak acid along with its weak conjugate base. Okay, keeps the pH steady. Okay, and remember for your exam, pH is minus the log of the hydrogen ion concentration. So good equation to know. Bless you. And then one final thing, I'll give you this equation on the exam. There's something called the Henderson-Hasselbalch Equation. So I'll give you this on the exam, but I want you to remember you want to use this equation for buffers. Okay, if you have the presence of a conjugate acid if you have the presence of a conjugate base, then you will use this equation. And the equation is this. pH is equal to pKa plus the log of, okay, here, the acid. Drop the acid in the denominator and the conjugate base in the numerator. So this equation is apt. This equation is properly used to get the pH when you have the conjugates. And usually when you have the conjugates, that is a buffer. Okay. So this equation is best utilized for a buffer. I'll give you this, but it will be good to memorize. I have a video where we can derive this. If you ever have some time, I know everyone is busy. You'll be surprised how easy it is to derive this equation. Okay. So we'll use this for buffers, and pH is equal to pKa plus the log of A minus conjugate base over HA conjugate acid. And don't forget what pKa is. If pH is minus the log of H3O plus, pKa is the minus the log of Ka. Okay, this little p stands for power. Okay, there's no units, it's just power. The power of H plus, the power of OH minus, the power of your Ka, power of your Ka, the power of your Kb. Okay, that little p just means minus the log of whatever. So this is our quick review of Monday's class. Let's move on here. Okay, so the new material actually is focusing on this thing called a titration. Unfortunately, I don't think you guys did a titration in Chem 1. That's because of the pandemic. So this pandemic robbed you of the ability to do a titration. It's an interesting thing to do, so let's go over titration right now. Okay. So let me draw a titration setup. So these are the problems that you'll do on Friday. They can be a little tricky. All right, so let's figure out how to navigate this properly. The first thing here is the titration setup is right here. You have a long piece of glassware, and I know I'm going to spill, and God forbid I may break the glassware. This long piece of glassware is called a burette. Okay, that's a burette. So it has a little thing there. You can turn it on and then turn it off. Has little volume markings. This goes all the way up to 50 mLs. So this long, slender piece of glassware is called a burette. I'm just going to try to draw that here. It's a burette. Okay. So in this burette, we can put some chemicals. Here we're focusing on acid-base titrations. Okay, so here in the burette, we're going to put an acid, and we'll titrate it. You know what titrate is? Little bit, and then a little bit, and then another little bit, and then another little bit. Keep on doing it, okay? A little bit, then a little bit, then a little bit, and you get a titration curve. And then you're going to titrate it to this thing here in the flask. Okay, so let's draw the flask. Obviously, this is the flask, okay? Erlenmeyer flask. A couple of terms here. What we are putting in. Okay, what we're putting in, drop by drop by drop by drop, what we're putting in, we're going to call that the titrant. Okay, that's the term. So the thing that you fill up the burette with the liquid is called a titrant. Remember, this is the one you're going to add incrementally. Okay? Called a titrant. That's called a titrant. Okay, this is the thing that we're going to go little bit by little bit each and every time. That's what we're titrating in. So that's titrant. Okay, so what could be our titrant? Remember, we're doing acid-base titrations, right? So our titrant could be the strong acid. It could be the strong base. Okay. It could also be the weak acid or the weak base. And then what do we titrate that to? We titrate it to the titrand. Okay, that's the liquid in the flask. So we have titrant goes to titrand. That's what this thing is called, the titrand. Okay, so we're going to go drop by drop, itty bitty by itty bitty, strong acid to strong base, strong acid to weak base, all the different combinations, right? We're doing acid-base titrations. So what could the titrand be? Okay, it can be the strong acid to the strong base. It could be the strong base to the weak acid. It could be the weak acid to the strong base. Okay, all the different combinations that you can think of. It could be the weak acid to the weak base. Okay, so all the different combinations could represent the titrand. And the titrant is what we inject. Okay, we inject little bit by little bit. Okay, little bit at a time, little bit at a time, little bit at a time. Okay. So all the different combinations, they're kind of shown here. All right. So I'll let you guys read that. But you know, all the different scenarios between, for example, strong acid, strong base, or let's say a strong base with a weak acid. So we will titrate or add a little bit at a time. Okay, a little bit at a time. There is another term that I want you guys to know, and that's called equivalence point. Equivalence point. That is when these two, titrant and titrand, are equal to one another. So I'll say that's when the concentration of the titrant equals to the concentration of the titrand. That's called the equivalence point. Okay, equal number of moles. All right. So you'll have a ton of these problems that you'll do on Friday. So work with your partner and check your answers with mine. All right, let's do a titration here. So Larissa set this up for me. Okay, so let's see if I'll do it here. So here's my titrand. This is just water. Okay, so I'm going to add some vinegar to this. Okay, so you guys can relax a little bit. So vinegar, another name for vinegar is acetic acid. So let's add about 5 mils of this vinegar. So essentially acetic acid. So 1, 2, 3. This is the titrand, remember. 4. And this will be 5 finally. Right, so acetic acid is a weak acid, right? Remember? I'm going to add a little dye here. Okay, this is an indicator. It's called phenolphthalein, and it's just an indicator. Okay, it's going to change color when the reaction is complete. Okay, that's all it is. Otherwise, you see this is colorless, and this, my titrant, is also colorless. How am I supposed to know when the reaction is done or not? So we add a little dye, also known as an indicator. So I'll add 2 drops. That's all you need. All right, so acetic acid, or weak acid, also known as vinegar, is done. It's our titrant. I'm going to titrate this with the strong base sodium hydroxide. Okay? What I like to do, and when I tell students at Chem Lab, I tell them fill it all the way up. Fill this all the way up. So that, you don't want to measure your volume. It's easy if you fill it all the way up. You can just read it. Ah, I added 17 mils. Oh, I added 26 mils. So let's fill this up. This goes all the way up to 50 mLs. So So this is your standard acid-base titration. My sodium hydroxide is a strong base. Okay. It's a little bit over the 0 mark. So, okay. One thing I want to tell you guys about the Burette, this piece of glassware, is that it's not meant to be very accurate. Okay, titrations you're supposed to do really fast. And so, like, oh, I got to get it to exactly, 0.5 mils. No, okay, it's like zoop, okay, zoop, okay, you'll see. And another thing is you can read this to 2 decimal places. Okay, you read this to 2 decimal places. Actually, you read this to 3 decimal places. I'm sorry. If you take analytical chemistry taught by Dr. Hooper, you'll know more about, the accuracy. You can read this and all that stuff, but you can read this to 3 decimal places. Yeah. Right. So, all right. Here's my sodium hydroxide. This is called the titrant. It's the strong base. Here is my vinegar. We'll call it acetic acid. That's my weak acid. So I'm titrating a strong base to a weak acid. And you do this, I'm not going to just turn this on and let it drip, okay, let it like a water faucet. No, you do this slowly, incrementally. Just try not to mess this up, BJ. Okay. So you do this like 0.5 mils at a time. Okay. So you do 0.5 mils, and then you shake it. Okay. And then you do another 0.5 mils, then you shake it. Okay. Not making sure it's exactly 0.5 mils. Okay. I'm reading this line. You guys can't read it because the volume readings are facing me. Okay. So you can do 0.5 mils at a time. You can do 1 mil at a time. You keep on doing this. Okay. So what do you think is happening as I add the base to this weak acid? Okay. The pH is going up, right? pH is going up. All right. So we're going to do this. Another thing I tell students, when they do titrations, you've got to be very patient. Okay? So, keep on doing this. Well, you may be asking yourself the question, when do I end? When does this stop? Right? So usually what we do in the lab, if you do this, we connect it to a computer, and that will sort of profile or graph out the pH. But you're also, when you're done, you reach the equivalence point when this turns pink. Why do I say pink? Because that's the color of this indicator. Okay, that's how you tell this reaction is over. Okay, when all of the titrant reacts with all of the titrand. They're all reacting. That's the equivalence point. Okay. At that point, there is no excess. There's no excess titrant, which is NaOH. There's no excess titrand, which is acetic acid vinegar. So that's why we add the indicator. So let's do 1 mil at a time. And this is also really kind of a knack. Okay. And a lot of students do this. They overshoot. This is a problem, and I'm pretty sure I will also overshoot my titrations. So that when you add too much, it's going to be too pink. Okay? You don't want too much of a color. You want just enough so that they are equal to one another. Well, this is really exciting and gripping chemistry, I'm sure. And I'm getting impatient, so I can just stop. Is this even working?
I see pink when it's
Yeah.
going in there, but it's just not the whole thing.
Yeah, it's got to be the slightest pink possible. Such that it turns the faintest pink. See, if it gets any more pinker, then you added too much of this. So that's the trick. Okay, that's the trick. And that's the rub. Okay, it's getting there. It's getting there. So this is more art than science, right? At this point, I would probably do 1 mil at a time. Almost there. I feel it. I should ask Larissa to make more of this. So anyways, you wait for this to become pink, and I'm a little worried I'm running out of this titrant, so. No, this didn't work. Oh well, I'm going to add everything. So eventually it's going to turn pink. And we wanted the slightest bit of pink. There.
Yeah, there you go.
It did work.
Yeah.
Yeah. So that is 50 mils. What the? It turned.
Now it's fine.
Oh, this titration didn't work. I don't think it worked.
We were all excited for a minute.
that's what's wrong with this.
Yeah, let's see what stays.
Yeah, but what's wrong with this color?
It's too dark.
Yeah.
Too dark is the right answer. So definitely, did we exceed the equivalence point? Yes or no?
Yeah.
Yes.
More than a little bit, yes. Okay, so, right. So, right, see, that's the purpose of this indicator. So there's 3 phases to this, okay? There's 3 phases to this titration. There's before the equivalence point. I'll call it EP. There was at the equivalence point. That is when it turns just pink and doesn't go away, just pink, okay? Slight pink. That's what I tell students, the slightest bit of pink. And most of the students will just get it to this color. Oh, done. No, the slightest bit of pink. You add 1 extra drop, you're after the equivalence point. So that's the tricky thing. That's why I was telling you guys this is more of an art than science, right? Okay. And then phase 3 is what you see here is after the equivalence point. After the equivalence point. Okay. And the specific example in this demonstration was the strong base titrated to a weak acid. Okay. So there's before the equivalence point, at the equivalence point, after the equivalence point. The strong base was the titrant. The weak acid, the vinegar, was your titrand sitting in the flask. So what's the pH? Okay, that is what you will have to calculate in this Friday's problem set. Okay, what is the pH before the equivalence, at the equivalence, and then after the equivalence? All right, and not just this combination, but you will see there's other combinations. They may ask you what is, they may throw at you something like the opposite. They may throw a strong acid titrated to a weak base. Okay, right? They may throw something at you for these problem sets, a weak acid titrated to a weak base. Okay, so all the scenarios, all the combinations you can think of. All right, that's what a titration is. All right. So let's do a titration problem here. All right, here. My notes. Oh well. All right, exactly 100 milliliters of HNO2 is titrated with 0.10 molar NaOH. Okay, so what is the initial pH? All right, so HNO2. I need to know the pKa here. Josh, do you happen to look in your textbook the Ka for HNO2? Or wait a second. I should be able to find it, Josh. Here. It's in my past notes here. HNO2. No? Yes? Is that something that you can see in your textbook?
What page it was on?
Chapter. Chapter 15. Oh well.
4.5 times 10 to the negative 4.
Awesome. Very good. Thank you so much. Okay. Nitrous acid. Right. That's what I was missing. So I'll give you this pKa on the exam. It was on the table in chapter 15?
Yeah.
Okay.
Table 15.3.
Table 15.3. Awesome. Thank you so much. All right. He's awesome. Okay. exactly 100 milliliters of 0.10 molar HNO2 is titrated with 0.10 molar NaOH, strong base. Okay, so what is the initial pH? The reason why I asked Joshua back there to search for this is because HNO2 is a weak acid. This is called nitrous acid, by the way. Okay. So the initial pH, nothing is added. Nothing is added. So you will just do your ice table. Hopefully by next lecture I'll be prepared with Ka values, but he got me there. Lifeline came through. All right, so the Ka here is 4.5 times 10 to the minus 4. All right, we have 0.10 molar ICE. Okay, initially minus X plus X plus X. So this bottle of nitrous acid, that's 0.10 molar, is not really 100% 0.10 molar nitrous acid. There's a little bit of H plus and a little bit of nitrite ion. So we have 0.10 minus X plus X plus X. Okay, this is the initial pH. Okay, nothing has been added. We have not added anything of the titrant. Right, so our Ka here is concentration of NO2 minus times the concentration of H3O plus divided by the concentration of HNO2. So 4.5 times 10 to the minus 4 equals, at equilibrium, the NO2 minus is X, the H3O plus is X. So X times X is X squared. And this is 0.10 minus X. Okay, let's go ahead and assume X is small. Okay, so low ionization assumption. So assuming X is small, 0.10 minus X is 0.10. Okay, so 4.5 times 10 to the minus 4 equals X squared divided by 0.10. This is the assumption that we're making. So let's solve for X here. So 4.5 times 10 to the minus 4 times 0.10. Let's go ahead and square root that to get our value of X. Realizing that X that we get is this X here, which is the concentration of H3O plus at equilibrium. So I do have a calculator here. 4.5 times 10 to the minus 4 times 0.10. And let's square root that. Where's the square root button on this thing? Oh, wow. Oh, here it is. Okay, square root of the answer. 6.71 times 10 to the minus 3. Here you want to put the units of big M, molar. And the pH is going to be the minus log of that. pH of minus log 6.71 times 10 to the minus 3, because it's minus the log of H3O plus concentration. And doing that on our calculator, okay, minus the log is going to be 2.17. So initially, 0.10 concentration of nitrous acid has a pH of 2.17. Part B is when things get interesting. Sorry?
When you assume X, do we have to go back and check it, or just?
We can go and check it. That's it's always very safe to do that. So yeah, let's test our assumption. The formula here is And remember, Adriana, our cutoff is 5%. So our X divided by the concentration of our acid. So our X here is 6.71 times 10 to the minus 3. What's our initial concentration? 0.10 times 100. Okay, I'm feeling this is going to be below 5%. 0.00671. 0.10. 6.7%. So technically we should use the quadratic equation here, but I'll just go ahead and move on, okay? All right. So if this is less than 5%, then this is fine. We can make this assumption, but it's over 5% by a little bit, so technically this assumption failed. And then you can't use this. You'll have to solve using the quadratic, but I won't do that, and you won't have to do that on the exam, okay? But it's good. Thank you also for letting us know about that, all right? So the assumption here is 5%. But let's just go ahead and say this is 2.17, all right, and move on. All right, the last 5 minutes or so of class. What is the pH when we add 80 mils of NaOH? Okay, so now we're adding 80 mils. That's a lot, okay? So when we add 80 mils, first of all, what I want you guys to do is write the equation. The equation is this: HNO2 plus NaOH. You can just write it as OH minus, okay? Because the Na plus is a spectator ion. That's at an equilibrium. That is a powerful base. This is a weak acid. So you're going to get H2O plus NO2 minus, okay? So that is our equation. And so here we have the concentration of OH minus. So we have 80 milliliters. What's the concentration of the bottle? 80 mils of NaOH. The concentration of the bottle is 0.10 molar. What's our final volume? 80 mils plus the 100 mils sitting here. So what's our total volume? 180 mils. Very good. Okay, so notice here, something very nice happens. The mils cancel. Okay. And so we're left with our final units of big M. So 80 times 0.10 divided by 180. Okay, the final concentration after you add the 80 milliliters is 0.0444 big M, moles over liter. Let's do the same thing for our concentration of HNO2. This is a weak acid. This is a weak acid. So here we have 100 milliliters of 0.10 molar HNO2. Okay, what's our total volume after we add all these two together? 180. Okay, so 100 times 0.1 divided by 180. The final concentration of this acid, weak acid, is 0.0556 big M. All right, so now we'll put that into our ice table. Let me rewrite this equation. Just rewriting this equation. HNO2 plus OH minus. Remember, the Na plus is just a spectator ion. The OH minus is going to, strong base, it's going to grab that H plus. HNO2 weak acid will also give that H plus. and we are left with H2O plus NO2. And this is all happening in water. Okay, water is a liquid. All of this is happening in the solvent of water. All right, HNO2, after mixing, we have a concentration of 0.0556. And here, OH minus, we have a concentration of 0.044 M. Okay, kind of setting up our ice table here. All right, initially this is, well, we don't care about water, it's a liquid. Okay, initially we have that. Okay, so what will be the change? Okay, well, do you agree with me that OH minus is a strong base? So how much OH minus will be consumed? It's a strong base, so how much? Will there be any left over? It's a strong base. Anything left over? A strong base. Okay, how much OH minus will be eaten up? It's a strong base, so all of it will be eaten up. All of it. Okay, it's a strong base. It's all gone. Okay, you never have anything strong left over. So it's all going to take all of it. How much is all of it? 0.0444, all of it. So 0.0556 minus 0.0444. All right. So at equilibrium, you will have HNO2 at 0.112 big M. This will be 0. And then you'll have NO2 minus at 0.044. Okay? So now you have at equilibrium this concentration of HNO2, this concentration of NO2 minus. You will use Henderson-Hasselbalch. Okay? And we will do that on Friday's class. We'll complete this. Okay? So we'll use the Henderson-Hasselbalch equation to get your final pH for this problem, to get that answer. Okay? So we're at the last step, and the last step is to use the Henderson-Hasselbalch. Why? You plug that in, you plug that in, you have a buffer. Okay? All right, I'll see you all on Friday. Have a good day.